The vector space axioms say that some of the familiar properties of column vector addition and column vector scalar multiplication actually hold in every vector space. But there are some familiar properties of column vector addition and scalar multiplication which aren't found amongst the vector space axioms. For example, if you multiply a column vector by 0, like this for example, what you get is always the same as the 0 vector. Or, if you multiply a column vector by -1, and you add it to that same column vector, again, you always get the 0 vector. But you won't find those properties amongst the list of vector space axioms. So are they special properties that just hold for column vectors, or must they hold in every vector space? Well, the only thing we can say about an arbitrary vector space is that it obeys the vector space axioms. So in this lecture, we're going to use those vector space axioms to show that these two properties are in fact true in every single vector space. Here's the first of those properties, written down as a lemma. It says that if you have any vector space V and any element, little v, in big V, then the scalar multiple 0 times V is equal to the 0 vector in the vector space capital V. So be careful that you understand what the notation here is saying. On the left-hand side of that equality, you've got a scalar multiple of the vector little v by the scalar 0. On the right-hand side of that equality, you've got the 0 vector, which is given in the definition of a vector space. So it's not obvious that those two things should be the same. In order to prove it, we're going to use the vector space axioms. And I've copied the vector space axioms for you down there at the bottom right of this slide. So to begin our proof, let's begin with 0 times v and rewrite that as 0 plus 0 times v. We can do that simply because 0 plus 0 is equal to 0. Now we're going to apply Axiom 7, which allows us to distribute scalar addition over scalar multiplication. So that is Axiom 7 down there. Okay, now what Axiom 2 tells us is that for every vector in V, there is an additive inverse for that vector. In other words, you can find a thing x such that when you add it on the left, you get the 0 vector. So Axiom 2 says there is an element x of V such that x plus 0 times v is equal to the 0 vector, 0 subscript v. I hope I've made those visually different. We're using the Axiom 2 applied to the vector 0 times v, whatever it is. And it tells us there's an additive inverse x such that when you add it, you end up with the 0 vector in your vector space. We're now going to add this vector x to the left of this both sides of this equation. So when we do that, we get x plus 0 times v on the left, and on the right we get x plus 0 times v plus 0 times v. Okay, next let's examine what's on the left. On the left of this equality, that is 0 sub v by definition of x. And on the right, we're going to use the Associativity Law for vector addition. So I can rewrite this as x plus 0 times v in brackets plus 0 times v. So that was a use of Axiom 3. Okay, we can do a little bit more writing on a little bit more rewriting. On the left we have the 0 vector, 0 sub v. And here on the right, x plus 0v, well again this is equal to the 0 vector, 0 sub v by definition of x. So we've got 0 sub v, the 0 vector, plus the scalar multiple 0 times v. Okay, one more line then. On the left we have the 0 vector, and on the right we have something, we have the 0 vector added to something. If we just take a look here at Axiom 1, Axiom 1 says that when you add the 0 vector on the left, you don't change the thing you added it to. So on the right hand side here we would just have 0 times v, and again this is by this time axiom number 1. And we're done. We've proved what we were supposed to prove. On the left you have the 0 vector, and on the right you have 0 times our vector v. So to try and distinguish a little bit more clearly between what is the 0 vector and what is a scalar multiple of a vector v, I'm going to underline my vectors just to remind me that they are vectors. So whenever we have a scalar multiplication into a vector, I'm going to underline that vector. So you'll see in typeset notes often we use a bold font for vectors just to distinguish them visually. And when we write on a blackboard or on a slide, we'll often use underlines to remind ourselves or to give a visual cue that something is a vector. So this is purely notation, but hopefully it helps distinguish a little bit more clearly between what is the 0 vector in a vector space and what is a scalar multiple of something, of some vector. Okay, there we go. Right, so we've proved this first lemma. Let's now move on and prove the other one, which I mentioned on our first slide, which was that if you have any vector space V and any element x in V, then x plus minus 1 times x is equal to the 0 vector. So we're going to attempt a proof of this, again using only the vector space axioms. So we need to examine this thing here, x plus minus 1 times x. Well, x plus minus 1 times x is the same as 1 times x plus minus 1 times x. Again, I've copied at the bottom of the screen the vector space axioms, and you will see that axiom 5 there tells you that when you scalar multiply by 1, you don't change anything. Okay, next we're going to gather together these two scalars here. We can rewrite this as 1 plus minus 1 times x, and the reason we can do that is because axiom 7 says we can. So that's an instance of axiom 7. Okay, next what do we have here? We have 1 plus minus 1. This is the addition of 1 and minus 1 in our field f. And of course the answer to that is 0. So what we have here is 0 times the vector x. And this is true just because in f, our field, 1 plus minus 1 equals 0. Okay, but our previous lemma tells us that this is equal to the 0 vector in our vector space V. So by the previous lemma. Okay, we're done.